Okay, it's 1 o'clock now, so we'll try and get started with the webinar from Chris on interfacing Python to other languages. So thank you all for joining the next of these RSE webinars. I hope you find it interesting. One thing I would say is that in terms of asking questions, it's probably easiest to type your question into the chat window, and then I'll make sure Chris is aware of it and make sure it's repeated for the recording. That is the other thing to note is the session's being recorded, and we'll put it up on the RSE website as soon as we've converted it into a YouTube video afterwards. So welcome to Chris, who's here from the University of Cambridge, who bravely was one of the first people his head up to present one of these RSE webinars. So I'll hand over to him now, and we'll go from there.
Okay, thanks, Andy. I'll just switch over. So I'm going to talk today about interfacing Python to other languages, as Andy said. Okay, so this is going to be quite a technical seminar. The trouble with that, of course, is it's very difficult to know what level to pitch things at, and everybody has different expectations. Some people probably know nothing about this topic, and other people already have some experience. So I hope I'm not going to disappoint too many people by keeping it hopefully fairly simple, and we'll see how we go as we go along. But please do ask, as Andy says, please ask questions in the chat channel or if you have any comments. I've got a Git repository which goes along with it with some examples in it which you can look at, which is there on the front slide. Perhaps we should post that into the chat channel actually, but I can do that later. Probably something you want to look at later. Also, you can email me or you can find me on UK RSE Slack if you want to ask me stuff later on. So Python, I think we all know Python pretty well. Probably most people here, I suspect, have used it a bit. Scripting language like MATLAB, very flexible, but sometimes can be a bit slow, just like MATLAB. If you have certain scientific calculations you want to do, you don't want to do them in Python always. So often you would like to use some existing code written in C or Fortran. And of course, things like NumPy or SciPy, they're written in C or Fortran, and you have a Python interface to them. But maybe you want to have an interface to your own code. Or you have some little piece of code in your Python that you want to speed up, and you want to add some compiled code to make that happen. And what I'm going to try and show you is it's actually quite easy to do both of these things using ctypes, which is built into Python. And I suppose what's got me started on thinking about this seminar at all is that we've had quite a lot of fun with a new package called pybind 11, which is really nice for interfacing C++. So I'll get onto that. Unfortunately, because it is quite sophisticated, I'll only really be able to scratch the surface, but hopefully it will give you a flavor of how things go with that. So if we're in the world of C, this is what a bit of C code might look like. Again, it's a bit difficult to know how to pitch things for a slide in a seminar, because you want to write some code which is complete, and yet to get it also to fit on a slide is quite hard. So this is a very simple subroutine, which I think you can probably see what it does. It just takes some input data and it takes something, a pointer to some data, and adds something else to it. And there's an integer n which tells you how many data points. So out data gets in data added to it. So very simple. And if you wanted to compile that with a GCC or something, you typically just type gcc -shared -fpic -o mylib.so mylib.c, if that was in a file called mylib.c. And what that does is it will compile it to a shared object instead of just compiling it to a usual binary. And you can then look and see what symbols are in that file by using the Unix utility nm, which just stands for name. So it just gives you the name of all the symbols in the library. So what I'm going to do is just quickly show you that to see how you do that, because I'd like to have live demos, because I know they're very risky, but we should do it. So yeah, what you would do, I've got some example here, and I've got the code in mylib.c. There it is. And I've got some, that's compiled it. And if I do nm-a, get the symbols from the library, gives me a load of stuff. But what you'll notice is somewhere in the middle of all that, there is the symbol add, which is basically the address of our function add, which we've defined up here. So the problem really is just how to get Python to go to that address, supply the right data, and call that function. And fortunately, that's something which is already built into Python with a library called ctypes. Now, just to show that I'm not prejudiced, I'm going to do this exactly the same thing with Fortran. We can do the same. Here's the same routine written in Fortran. So for those of you who are keen on it, it's very similar. You will just compile it in the same way. And let me just show you that. Yeah, so there is the Fortran example. Does the same kind of thing, and we can compile that in the same way, and you'll get a similar symbol. What you notice in Fortran, which is slightly different, is that it has an underscore attached to the symbol as well. But that's just the way that the compiler does the symbols for Fortran. So we've got these two things. We can write it in Fortran, we can write it in C. It's very simple because it's got a fixed interface. You know exactly what you're putting in. You're putting in a pointer to a double precision number, 2 pointers to double precision numbers, and an integer. So calling that from Python. Here's an example of how to do it. So you have to import a library called ctypes, and then it has a way to load the library into memory. So it's called cdll, loads that library into memory. And then it's very natural in a way, it just becomes a member function of that object when you load it in is add. And somehow we've got to send the right kind of data. So there's some kind of casting that you have to do to send the data in the right format. So what you'll see is this array X here has got which is a numpy array, has got some a way to send it as a pointer to a C double. And that should just work, and indeed it does. So I'm going to just show you that actually working. So there it is, that's the code, and if I just run that, it adds. So I put in, yeah, so it basically just adds together. Right. Okay, so the first time it's starting with 0, and then I'm actually calling it twice in this example. So it's first of all it's starting from 0, then adding it once, and then adding it again. So you can see it's working. So that's with C. The same thing with Fortran. It behaves exactly the same way. The only slight difference with Fortran is that because it sends things by reference, you have to do things slightly differently. And as you remember, the symbol is no longer just add, it's got to add with an underscore. So yeah, there's the same thing for Fortran. Like I said, you have to send things by reference. So, but fortunately, there's a nice thing in ctypes to let you do that. And you change the name of the symbol from add to add with an underscore. So this is all fairly straightforward, fairly easy to do. You write your code in C or Fortran, you compile it as a shared object, and then you can just call it directly by importing it with ctypes. So I suspect some of you have probably done this before, and I'm probably just telling you something you already know. But for some of you, maybe this is new, and it's just a really easy way to call C or Fortran, or anything really which has got a fixed interface. There is another way to go, which is a sort of more recent addition to the Python world, which is this thing called cffi. The cffi is not included as a sort of core part of Python, but you can install it pretty easily with pip install. And it's very similar to ctypes in some ways, but it has what they call two different modes, API mode and ABI mode. So one is the sort of application mode, and the other one is the binary mode, where so one is where it looks at that you can look at a header, and the other one is where you actually have to have exactly the right binary representation. So I suppose ctypes is the sort of ABI type model where you know exactly what you're sending. But the nice thing about the API mode is that you can also just include the header files of your C. So if you know what the signature is, you can just include it and it will deal with it. So this is just showing here the ABI mode, which is very similar to ctypes. Somehow you import cffi. You have to tell it what the function signature looks like. There's a slightly different way of casting your types to the right kind of data, and then it will do exactly the same thing. The API mode actually lets you do something a bit more sophisticated. It lets you actually compile some code from Python. So you could actually include your entire code as part of the Python script. So for example, this might be something where you just want to speed up a little bit of the code by having your Python code by having something compiled in the middle, and you don't want to have an extra effort of compiling something externally. So you can do this. They kind of advise against it, and I can see why you don't want to do too much of this, but I think it's okay for small functions. And I think the real use for this is to provide a sort of interface layer between your Python and an existing C library. So it allows you to do that with a sort of more flexible way. So I can just do a quick demonstration of that as well. Excellent.
So there's a question here, Chris. Ben's asking, does that use its own compiler or a system one? So is there a compiler built into FFI, or is it calling out?
Yeah, right. So there's no compiler built into cffi. It will call out to whatever the system one is. Now, I'm not quite sure exactly how it does that, because very often when you're compiling these kind of libraries for Python, it will look at how Python was installed and use the same compiler that Python used when it was built. And that can cause a few little issues because it sometimes has some flags or some includes which you don't necessarily want. So I'm not totally sure about cffi. I certainly know that that's the case with pybind, which we'll come to in a bit. But I'll tell you what, why don't we just run it and we'll see what happens and see what it says. So here is the API sample. And if I just run that, what's it called? API example. So now you can see exactly what it does. And I'm not sure if that is using it could be using the, actually I'm not totally sure where it gets all the flags from. These could be the flags which were used. It probably looks like they could be the flags which were used when Python itself was, yeah, it looks like it, because when Python itself was built. So that's often what these tools tend to do, because I suppose they have no other way of knowing what compilers are available on the system. So yeah, so that's what it's doing. And you'll notice actually what it's done here is it's built a shared object library for us here, which it can then call. So it's basically doing the stuff which I did manually before. It's just doing it for me without me having to think too much about it. Right, okay, so I think I'll probably just summarize a little bit at this point. So if you're just interfacing C or Fortran, because it's a fixed interface and you know exactly what, you should sort of know exactly what's happening, it's pretty easy to do actually. You can use ctypes and it's built into Python, so that's got a real advantage. You don't have to worry about installing dependencies. There's also this thing called cffi, which is a bit more sophisticated. It will compile stuff for you. It's quite nice for example, we've got some stuff where we have some generated code in one of our projects, and you want to run some unit tests. So then you want to actually incorporate the generated code somehow and call it from Python. So that's also possible to do with cffi. I'm going to move on now to a topic a bit more abstract in a way, which is can we not just compile Python? So I think this has often actually been a dream since the beginning of for many years with Python. So why don't we just compile it, have a compiled version? And this project, which has come out recently, I really like, because what it does is it actually allows you to just put a decorator on a function, and it will then go off and compile that, and then you can just use it totally transparently. So you wouldn't even know whether or not it was running in pure Python mode or whether it was running in compiled mode. In order to do this, it does use a few tricks, and of course you can't just do anything in this and get it to work. So you might expect it doesn't always work, but sometimes when it does work, you can get a good advantage from it. So this is kind of the case where you just want to speed up a bit of your Python code. Yeah, so number. I'm just going to show you how that works. So yeah, there's a very simple example here. You import this from number, import JIT, put the JIT decorator onto the function that you're interested in. So this is just a function which takes a whole lot of random numbers and calculates the distance between them. So if you imagine they're points in 3D space. And I've told it to do for 1,000 points. The nice thing about number is what it actually does is it compiles it in memory. So there's no writing to disk. It's all done with an LLVM. And if I just run, what I'm going to do is I'll just edit that file, and I'll take off the decorator. Just put a comment in there for now. And then let's run it. And I'll time it as well. So see how long it takes to do that. I'm just running it as pure Python. It takes a little while.
So, Chris, I have a question here. This is
right.
NumPy analog, which you'd expect to be optimized and compiled anyway. So I'm assuming you're going to show some benefit. So where's the benefit? How is it getting that benefit?
Sorry, beg your pardon?
So you're using a function from NumPy, which should be compiled and optimized anyway in some sense, right? It's probably coming,
that's right.
It's probably coming from MKL. So
yeah, absolutely.
Why does compiling with number have any effect?
Well, I'll show you that it does. And the reason that compiling with number has an effect here is probably because the code is not that well written in this case. What it's doing, if you look at it, it's doing for I in range n, for j in range n. So it's actually looping in Python over. Okay, I've messed up here because I've left in something which only works when you've actually got. Let me just fix this quickly. We can't look at it if we haven't actually compiled it. So yeah, so it's taking about 13 seconds to run. And the reason why it's taking a while is because it has to loop over this I and j range in Python. Yes, and indeed the inner call to numpy linalg norm is of course optimized and is written in probably in C or as you say with MKL, but it's only using that on very small vectors of size 3 in this case. Yeah. So basically, what this is doing is it's calling 1,000 times 1,000 this call. So it's 1,000,000 times it's calling the NumPy routine, but from Python. Yeah, does that make sense, Andy?
Thanks.
So now what I'll do is I'll put the decorator back on, and what we should see is that it will now compile the whole of that routine. And it should be much faster. Of course, there's an overhead for actually. Oh, that was fast. Right. Okay. I've again need to comment out this stuff. Yeah. So now it's taking 1.6 seconds instead of 13 seconds, and still doing the same thing. What this does, in fact, here these lines actually shows you what the code looks like. So. You can see here there's a whole load of, if you're really interested in it, you can find out exactly what it's doing. And somewhere in the middle of all that will be the call to that NumPy routine. Yeah. So it's really nice because it does it all in memory. You don't have to have a disk. So it's actually nice somehow for applications where you're not sure what your file system might be. So you can do it in memory. So it's something I'm very happy with. Let's just go back to the. So I'll come back to that a little bit later on because it's very useful for some other things too. So if we want to talk about C++, it's kind of a natural partner for Python because it's object-oriented, and we might not just call a simple function.
Question, so I'll interrupt you.
Yeah.
Edo's asking, are types automatically inferred in number?
In number, yeah, that's an interesting question, because what actually happens? What actually happens with number is that it looks really simple, doesn't it? You just well, it looks really simple. You're just applying this decorator at JIT, and it goes off and does it. And of course, let's say, how does it know what n is, right? Is n going to be, because in Python, n in this example could be a float, it could be an integer, it could be a complex number, it could be an object, it could be all sorts of different things. And Python just deals with it when the function gets called. But of course, if I'm now compiling this, I need to know what type n is. So how does it do it? And how it does it is when you actually call it for the first time, it looks and sees what type n is. And then it goes and does the JIT compilation. So it doesn't actually pre-compile it, it literally does just-in-time compilation when you call it. So if I were to do another call of it, n equals 10.0, let's say, and call it again, okay, my code would probably crash. But what would happen is it would go off and recompile all this with n as a float. So it would recompile it. Yeah. So yeah, that's how it works in this case. It doesn't know what the type is until you call it, and then it compiles it. Does that answer the question?
So Edo says, Alan, what about I and J?
Well, I guess it probably knows about that too. Perhaps because range should always return integer. So in a way, what numba is doing is it's sort of re-implementing Python. So if it sees something like range, it probably knows that this can only produce integers. So that's probably how it works. Yeah. I mean, I'm not an expert about number. I just use it, and it's a really cool project. I like it, but I don't know all the intricate details of how it actually translates. One thing I do know, which is quite interesting actually, is that something like this, where it calls out to NumPy, you can often get better performance by. So, okay, if you want to do a little experiment while we're here, we've got a few minutes. Let's do it. What I could do, we know that this norm thing is just like some maths, isn't it? So instead of writing that, I could say it's it's some kind of PTS I0 minus PTS A0 squared plus, I could do that. And often for these simple algorithms where you're just doing some kind of maths calculation like that, but that should do exactly the same, I guess. Or maybe I need a square root. I'm not sure whether norm has got a square root in it or not. Maybe it has. We could do that too. And these kind of maths algorithms, it's actually quicker to do this kind of thing. You find that that's actually runs faster. Yeah, see, that's a bit faster than the call out to NumPy. So actually, the effort of making a call to an external bit of code can be a bit of an overhead, especially for something that's quite simple, the kind of maths operation like this. If you just write it out by hand, often you get a bit of a performance boost. Yeah. Okay, I'm just going to move on a bit because otherwise we'll run out of time, and I've got a few more things to say. So let's switch back to the presentation again. Okay, as I was saying, I'm moving on to C++. It's a natural partner for Python because it has classes, and you've got methods which you may want to overload, and you want to call Python for C++ and C++ for Python. You've got so many different choices of things to do. It's much more complex. It's much more natural partner, but there's so much more that you can do, and it's going to be harder. still. Let's have a look how we can do it. So here's a similar kind of code that we were just looking at in number. And this time I'm going to return a standard vector double. So using STL, it's the usual thing to use in C++. Call this this function calculate distances. Maybe I've got some internal data already in this. This could be a class point cloud, and I've got some class data called points, which I've already loaded into it somehow. And here I'm just going to do the same kind of calculation. So you can see this is just I've made it linear, but it could be a two-dimensional array really. And I'm going to fill it up with, and I'll call some internal function distance, whatever that is, that will work out the distance between 2 points, right? And return this result. So that's the kind of code which I'd like to interface to Python. So there is this library called pybind 11, which we discovered it about a year ago or something. It's developed by some people at ETH Zurich, and it's really nice. It allows direct access from C++ classes to C++ classes from Python. It integrates with STL, standard vector, and so on, and maps them onto Python native objects. So standard vector becomes a list. I guess a standard map becomes a dict, and so on. What you do is you write some code, something like this in C++. Oh, you need the C++ 11, of course. Yes, I mentioned that already. Up here, you do need that. You include a couple of headers. So in this case, its own header, pybind11.h, and one for STL. And there's a macro which lets you define a module which will then work in Python. And it all looks, it's a bit kind of the mystery somehow how it's written, but on the other hand, you just follow the pattern and it works quite nicely. So there's a couple of things you have to do. For example, there's this .def which allows you to define functions, so, or class methods in this case, I suppose we should call them. So here's the definition of the constructor, and it says the constructor just takes a standard vector double, reference to a standard vector double. So that's how I would construct the class. And then it says there's also a class method called calculate distances, which is just mapped onto calculate distances. So this is the C++ name, and this is the Python name. So, right, what's that look like from the Python side? If I compile that bit of interface code, what will I do? I will just import, I will just say something like from point cloud, import point cloud, that imports it into Python. And here's the constructor. I will construct point cloud with a list of numbers. Remember, the STL vector maps onto a Python list, not to a NumPy array. So I have to give it a list. And then when I get the output from calculate distances, that will again return me a list because I told it it was going to return, return standard vector. So that will return me a list. And so I'm now feeding it back into NumPy to get it to look like a NumPy array. So I'll just go over and show you how that all works. Yeah, let's get out of this. So my C code, my C++ code, class point cloud, there's a constructor which just literally copies the values into a class variable down here. Here's the code that actually does the calculate distances, very similar to that number code we saw before in Python. And they've got a private method which never sees the light of day in Python. We just call that from inside the C++. Yeah. So what I will do. Oh yeah, and then underneath I've got the interface. So this is the interface to Python. Include the pybind 11 stuff and have this macro, and I just say, okay, I've got a constructor, and I've got a member function which I also want to expose to Python. Now the compilation is a little bit more difficult for this because you need to have the right header files available. You need to compile it. So usually it's better to use a setup.py file. It can get a bit tricky. You need to obviously tell it that it needs C++ 11. But I just set this up to work on my machine here, and I'll just do it like this. Okay, I'll just delete everything. And there we go. It compiles it for you with that setup.py. And again, you can see it's using the same settings that were used to compile compile Python in the first place, I guess. Yeah, that will produce an SO file in the folder build, which I've now also added to my Python path. So I just add that to my Python path. That should make it available. Test.cloud.py, I'll just run that. Okay, there we go. That ran and did pretty much exactly the same thing. That was only with 5 points, mind you, not 1,000, but it's just a demonstration. Otherwise, it just goes off the screen. So that was pybind 11. There's so much more you can do with it. Obviously, you can access not just functions, but you can also access data members. You can add extra Python-only members to a C++ class. So you've written something, you have a library in C++, but you'd like to sort of have a slightly different Python interface somehow. You can just write a Lambda function and stick it into that interface code. You can overload C++ virtual methods in Python. You can call Python from C++. There's a lot to take in, and I can't possibly describe it all just in half an hour. So I would say go to read the docs if you want to do something. You can also talk to me on Slack, or if you've got a serious project you want to do with it, it's best to just start simple and build it up. But it is really good. It's much better than some of the other alternatives which are on the market, like Swig, which we used in the past, but found it to be very cumbersome, and it's not really designed. It's designed for interfacing lots of different languages to Python, not specifically C++. Okay, so now I want to just move on to a sort of final topic,
Chris,
which is
a question here. So I'll comment anyway. So Edo says it seems very similar to Boost Python.
Yeah, it's based on Boost Python. In fact, it's a kind of updating of Boost Python, if you like. So yeah. So the other thing I could quickly demonstrate, actually, which I was going to do and I sort of forgot about there, is yeah. So the other nice thing, I don't know how many people have used the Eigen library in C++, but Eigen library is a really nice library for doing sort of mathematics and linear algebra type problems. So what you can do is I've got a version here which, rather than using standard vector, is using Eigen matrix. So Eigen matrix are double precision numbers, and you can probably be best to try this out yourselves later on if you have a look at my Git repository. But you can do basically exactly the same thing using Eigen as the sort of, instead of using standard vector and so on. And sorry for all these beeps. Okay, you will have a different interface. So I've now got a header for pybind 11, which knows about Eigen. And the nice thing about that is now you will have an interface which interfaces nicely onto NumPy, because the Eigen matrix or Eigen's matrix class or array class or vector class in Eigen maps directly onto NumPy, which is really nice. So it's a really nice interface between C++ and NumPy if you use Eigen in the C++ layer. Yeah, so that's also worth saying. Boost Python I haven't used, but I think this is really kind of the successor to it in a sense.
Right. So we do have another question as well that came up while you were answering that, which was from Fadi, who asked, do you know if there's a way to interface modern Fortran or OO Fortran with Python?
Yeah, I'm afraid I'm not really a Fortran person, so I couldn't say, but I'm not aware of anything. It's possible that you could do it, but it's not something that I'm, I suppose, particularly interested in myself. So yeah, I mean, if you could find out some information about that and maybe post it somewhere on the, for example, the Python channel of UK RSE Slack, it's kind of be a good place.
Thanks, Chris.
Okay, so yeah, go and read the docs. What I'm going to move on to now for the last little topic is callbacks. So this is something that we're kind of keen on with projects because we have a lot of this going on. And here's a sort of typical example. I've got some library, right? And it does something. I don't know what it does. Hard maths, we'll call it. And in the middle of that library, I want to call a kernel function. So there's some function x, and I've got to do something to x and return it back to my library. But I'd like to define that kernel function in Python, if possible. So how can I do that? So this is the sort of example of what I'd like to do. Import hard maths, define some kernel function that does something to some variable and returns it back. And then I'll call my hard maths library to do something, and I don't know, some parameters, but I'm going to give it that function as another parameter. Inside the sort of C library or Fortran or C++ or whatever it happens to be, it would look something like this. I've got some function pointer, f, and I'm doing something, and I want to call f, right? How can I do that? So there are various ways to do it. You can, for example, do it with pybind 11, and there is a way, what they call a trampoline class, to connect the Python callback, and it works pretty well. But the callback is still in Python, so it can slow things down. And obviously, with kernel function, it often tends to be the very core of what you're doing and gets in a sort of hot loop, called many, many times. So it's not always what you want to do. And what I would like to show you today is there's another way to do it. You can just-in-time compile it, or you can pre-compile it with numba. And you'll compile the Python to itself into a binary with a C interface, and then you can just call it from C. Obviously, in that case, you do need to know the signature and the address of where it is in memory, but it's all possible with numba. So here is hopefully an example of how you do that. Before, we had this thing called, we were importing this thing called JIT from numba, but now you can import something called cfunc. And what I'm doing here is I'm calling cfunc with a signature, which tells me what I'm expecting. So I'm expecting a pointer to double, or 2 pointers to double, and an integer, right? And now I say, okay, try and compile this bit of code called calculate distances, and do it with no Python. So that means it's got to be all just compiled up into C code. What you'll notice also now is that when these variables come in, they need to be somehow translated because they're just kind of raw pointers to C, to memory in C. And so there's this function in numba called carray, which effectively converts between a pointer and a numpy array. So it will basically turn what is a raw pointer coming into this function into a numpy array of the appropriate type and size. And then I can just do, as before, whatever I want to. And right, and then I will just, when it gets to this line, it will actually go and compile this and put it into memory. So somewhere, yeah, so then later on, I could give an example here, and this is just a sort of way to test it from Python. I can say, call this function. Right, but in fact, what you'd want to do is pass the address of this function to your C code and call it from C instead. So I'm just going to show you that. So what I've also put in here is it shows you the again the LLVM intermediate representation of what it's actually doing. It's again compiling it in memory, and here is in fact the memory address where the code is. So what you would do, in fact, I haven't put an example of this, but when you get this address of the function, you could send that off to a C library, and it would be able to call it. So just like a function, it basically is just a function pointer to that function in memory. So that's how you can send a kernel function into another code. I probably should work that up into a slightly more advanced example. So this is just showing you how to test it, but yeah, it works pretty nicely. So that's kind of a summary of where we're at with it all, I suppose. If you've got a simple call to C or Fortran, you can use ctypes or cffi. For C++, you can use pybind 11. It's pretty cool, does lots of things. JIT compilation I also like because it does it all in memory, and it has a C compatible interface that you can just call from C. And yeah, you can also do it with pybind 11 as well. And if it has a fixed interface, of course, you can still do it with ctypes too. But yeah. Right, okay, well, that's the end of my presentation. So I'm available for questions for a few minutes. And yeah, I'll be on the UK RSE Slack. So if you want to have a more extended discussion about it, or if you think about something that you haven't thought of yet. And
thanks, Chris. So Andy's asking, could you say anything about error handling?
Right, error handling. Well, certainly in pybind 11, there is a possibility, because it interfaces really nicely with C++ and with Python, you can throw errors in C and C++, and you can also throw them using the Python error handling system. So it actually integrates very well with both. In terms of doing it from C or Fortran, it's a little bit more basic, I guess. I suppose it's more difficult to think how that works. So if your code throws an error, it'll probably just crash, I guess. Yeah.
Okay. And Zednek asks, have you tried interfacing quad precision Fortran into Python?
No, I have not done that. But I tell you what I have just done recently is I've interfaced complex numbers from C, which is pretty similar kind of thing because it's 128 bits basically. And if you use cffi, you can map that nicely onto NumPy complex 128. So I guess it will just work if you're just using the fixed interfaces of ctypes or cffi. All you need to do is just say it's 128-bit float or whatever the NumPy type is for that, and it will just map seamlessly, I guess. It certainly works fine for complex numbers. So yeah.
Yeah, I guess what you need to know is position and length, right?
Yeah.
Dr. Fortran says, for Fortran, why not use the ISO-C binding module? This removes the name mangling.
Okay, well, the name mangling is just an underscore, and I'm not really interested in Fortran, so that's my answer to that.
Fair enough. And that's not really a question, but Casper's commenting that you can do CUDA in place as well if you happen to have a GPU card, a CUDA compatible GPU card.
That's something, again, I've not really investigated. So I know there's a lot of people who've done a lot more exciting things than I have probably. So yeah, if any of these, perhaps we should have a collection somewhere of all this information into one place. It'd be nice to have a little repository with some,
so
just a web.
So what I can do is, once we've got the recording up, I'll also add useful links that people submitted in the comments as part of the page where it has the sort of slides, the video, and then other things.
Yeah, so in terms of Python, Ryan, yeah, the thing about Python is it's another language, and one of the things that I'm kind of keen on in many ways is not having to learn a special language just to do this interfacing task. So I've really stuck to only using Python or C, C++, Fortran, because they're very standard, very widely used, and I don't want to have to bother to learn Python. I think it has similar performance, but yeah, I'd rather use the pybind 11 stuff and the number stuff.
Yeah, sorry, any comments on portability or robustness?
Right, well, yeah, there are some comments on portability and robustness. It's previously we were using Swig, which was very difficult to use, and the portability with that was quite painful. There's some nice things. For example, one of the things about numba that I said, because it compiles in memory, you don't need to have a a disk available. So that's really nice, especially on HPC systems where you're not sure necessarily where you can stick temporary files, or if there's, what's available in terms of file systems. It works. All this works nicely on macOS. I've used it on my laptop nicely. I haven't really tested under Windows, so of course that is. But it should all just work, especially the ctype stuff. I'm sure it's all fine. But I think generally it all just simply works. I've not had any problems with compatibility.
The question was from Ben on the maturity of the third-party product. I mean, it's a classic. One of these things is you find a useful tool out there, and how long is it going to live? I guess a useful open source tool.
Yeah, of course, it's always a worry. Something like ctypes, of course, is built into Python, so you don't need to worry too much about that. And it probably should be your first port of call if you're just doing something simple. cffi seems to be popular at the moment. I think it's got a good future ahead of it. And pybind, again, sometimes it's just a question of adoption. If a lot of people start adopting something, then it will become popular and it will get supported into the future. There certainly seems to be a very keen team behind the pybind 11 stuff at the moment, and we've been very happy with it ourselves. So I'm kind of hoping it will be supported into the future, since it does seem to be the successor to Boost Python. So yeah, it's always a worry, but of course, how could we say, I'm just trying to back what I think are the best horses.
Yeah, it always gives you a bit more confidence when these tools get adopted by something like NumFocus, which have some idea about sustainability going forward. Okay, does anybody else have any questions? No, I noticed a few people said thanks to Chris already. I'd just like to add thank you to Chris for agreeing to do this and a really interesting presentation. Oh, there you go. There's another question from Ryan. Can you get VM compilation warnings from numba?
I guess you can get something. I'll tell you what does happen. Obviously, if you type something in Python which it doesn't like, which it can't figure out how to compile, it will throw some kind of error. So yeah, it's not something I've really investigated too much, actually, how to get the compilation warnings from LLVM. You probably can. Yeah, be interesting to know about that. And also to set things like optimization flags and so on. Yeah, definitely. So I kind of feel like I'm still at the beginning of my journey with numba. There's a lot more to discover about it and to figure out how to get the best out of it. But it just seems like such a nice tool. I'm very keen on it. Yeah, it's a bit worrying, but not too worrying. Well, it's not just JIT compilation effects. So it's, very often we're doing ahead of time compilation, so what we call AOT, I suppose.
I get, Edo, I mean, I've got comments on that. It's a little bit, it's not that much different from normal compilation, right? A normal compilation, something compiles. It doesn't mean it's going to run correctly at runtime. You still have to check, and you'll still get runtime errors, right? There's just the errors are just in a different place, but that's always true of compiled languages and JIT. It's like compilation.
Yeah, I've also been a bit loose about saying things are JIT because quite often it's just I'd like to compile some Python up, often beforehand actually. So that last example with numba for the callbacks isn't really JIT; it's ahead of time compilation. Mm-hmm. Yeah, well, maybe you should switch to pybind.
I think compiling something that involves multiple languages can be inherently more complicated than have a.
Yeah.
From, right?
Of course, and I think everybody who uses C++ gets frustrated with the error messages, especially when you have heavily templated code. You can get pages and pages and pages of error messages, and it can be difficult to understand what's going on. One of the nice things about the pybind is that there's a really active channel, I think, on Gitter from the developers. So if you have a problem with it, they're pretty good at answering questions. So yeah.
Fine. I mean, what I would say is there's obviously a lot of interesting discussion going on in the comments. So please take that discussion over to the Slack channel. If you want to create to the Slack instance, the RSE one, if you want to create a Slack channel there to discuss these issues, please do, because I think there's a lot of interesting chat here. There's obviously people who are interested in have various experience with different tools and what that means for different codes.
Yeah, we could just use the Python channel. There's already a Python channel.
So once again, thank you, Chris. We'll stop there. Thank you, everybody.